If you've ever seen the movie Interstellar, at the end, there's a space station called Cooper Station. They say that it's orbiting Saturn. On this space station, people are able to walk around like normal, just like they would on Earth. If we watch this video, we can get an idea of what this space station looks like. It seems to me that the Cooper Station is shaped like a cylinder with people living on the inside of it. Something like ladybugs living on the inside of a pop can. However, if there's just a pop can floating around in space, then the inhabitants of that pop can will also just be floating around in space. We need to figure out how to create a habitat for these ladybugs to give them a sense of gravity. Some of you may already know that in order to do this, we can just give this giant pop can a spin. So today, we're going to look at the specific physics of this artificial gravity. But before we do that, we need to understand this idea of circular motion. So let's trace out the path of something moving around in a circle. So we know that if this object is moving around in a circle, it has some sort of velocity that is tangent to that circle. Now remember, tangent just means that this line will intersect this circle at a single point. It just barely kisses the edge of the circle. And at every point on this path, the velocity vector is going to be tangent to that path of the circle. So now let's look at some definitions. We remember from kinematics that velocity is speed with a given direction. And we also remember from kinematics that acceleration is just a change in velocity. This triangle represents the word change. So acceleration is a change in velocity. Around the circle, this object, whatever it may be, has a constant velocity. However, although the speed may be the same at every point along the circle, the direction is certainly changing. And because this direction is changing, it means that this velocity is changing. And if there's a change in velocity, it means there's an acceleration. Okay, let me say that again. So, the speed at every point, the tangential speed, is the same at every point around the circle. However, the direction is constantly changing as it moves around the circle. So because the direction is changing, the velocity is changing. And if the velocity is changing, then that means we have an acceleration. So we have to think about what is the direction of the changing velocity. Well, remember, changing velocity, we can rewrite this as acceleration. So what is the direction of the acceleration? Well, how does the velocity change? It turns out that the velocity first is going this way, then it's going this way. So the velocity changes from here to here. So that means that the direction of the acceleration at every point along the circle is directed towards the middle. Although the velocity is constant around the edge of the circle, there still is an acceleration that points towards the middle. And this acceleration has a fancy name. It's called the centripetal acceleration. Go ahead and say it. Centripetal acceleration. So let's see if we can develop an equation for this centripetal acceleration. I'm going to call centripetal acceleration A with a subscript of C, the centripetal acceleration. And we need to figure out what the centripetal acceleration is proportional to. This little symbol right here, the Greek letter alpha, in physics, it's a symbol for proportional to. So what is the acceleration, centripetal acceleration, proportional to? Well, let's consider this. You're driving in your car. First, let's look at velocity. If you're taking a corner, and you're taking this corner at a very slow speed, okay, what are you going to feel in your car compared to if you take this corner at a very high speed? Well, you're probably going to feel a greater centripetal acceleration. You're going to be thrown against your car door a little bit harder if you're going faster. So that means the greater the velocity that you take a corner, the greater the centripetal acceleration. And that means that they share a directly proportional relationship. Now let's look at another property of our circular motion. We can also change how tight the circle is, or the radius of a circle. So let's say you're going at a constant velocity, and you take this corner, as opposed to taking a corner that looks like that. So you're taking this corner at a constant velocity, or you're taking that corner at a constant velocity. Which one of these corresponds to a greater acceleration? Which one of these will you be thrown against the car door harder? Well, if you think about it, the one with the smaller radius, if this is the radius of the circle, the one with the smaller radius will result in a greater centripetal acceleration. So that means that they share an inversely proportional relationship. So as this number is smaller, it means that this number gets bigger. Okay? And as it turns out, as we do some experiments, the actual equation for the centripetal acceleration goes something like v squared over r. This is the equation for the centripetal acceleration. Well, hey, I know what you're saying now. Well, hey, wait a second. This thing has a mass. And if this mass is accelerating, well, that must mean mass times acceleration. That must mean there's some sort of centripetal force in this situation as well. Well, you're exactly right. So let's plug in the centripetal acceleration equation here into our centripetal force equation, and we're going to get something that looks like the centripetal force is equal to, keeping this m, now replacing this with v squared over r. V is the velocity around the edge. R is the radius of the circle that object is tracing out. So this is the centripetal force equation. We'll work more with the centripetal force tomorrow in class, but for now let's return to Cooper Station. So let's say we're returning to our pop can. Okay, but let's say we're looking at it from an edge-on view. So here's the space station in space, okay, floating around, spinning like this. But we're going to look at just the end if we have a little ladybug living on the inside of this water bottle spinning. Okay? So let's draw that picture. So let's say on our space station we want our inhabitants to experience an acceleration, a centripetal acceleration of 9.8 meters per second squared, which happens to be the same acceleration that they would experience if they were on Earth. The difference is that the Earth acceleration is from gravity because the Earth has a mass. This acceleration is because this person is moving around in a circular motion, and there's an acceleration of the floor up towards the center at every single point. Okay, so we're in space and we're spinning around. So let's say, I don't know, that our our space station has a radius. Let me do this in a different color here. Let's say that our space station has a radius of, let's say, a football field, about 100 meters. So that means from the diameter, so from one edge to the other, you could fit 2 football fields. So the radius is 100 meters, or 1 football field. And let's say we want to figure out what velocity do we need to spin our space station such that the acceleration, the centripetal acceleration that this person feels, is an acceleration similar to that of Earth. Well, let's look at our centripetal acceleration equation. We have centripetal acceleration is equal to v squared over r. Remember, we're solving for v, so we need to isolate v. So we're going to get v squared is equal to ac times r. And we need to square root both sides to eliminate this square. And we're going to get v is equal to the square root of our centripetal acceleration times the radius of our space station. So now all we have to do is plug in numbers here. We have velocity is the square root of 9.8 meters per second squared times our radius of 1 football field, or 100 meters. And if we plug this into our calculator, we are going to get an answer of 31.3 meters per second. So our spaceship needs to be spinning. So this little fella right here needs to be traveling at 31 meters per second. So just to review, in circular motion, something moves around in a circle, we're going to say it's at a constant speed. So because the direction is changing, it means the velocity is changing, and when there's a change in velocity, there's an acceleration. That centripetal acceleration is always pointed towards the center of the path that whatever it is taking. Also, recall that the equation for the centripetal acceleration is v squared over r, and that if we have a mass that is accelerating in the centripetal direction, that means there has to be some sort of centripetal force associated with it, and that equation is given by mv squared over r.